Bien, escribimos por favor. Y que ninguna. Bueno, Miguel, ¿nos escuchan por allá? No, no. No, yo ya entré y yo me escucho antes, entonces, pero hay, Emilio, ¿podrías decir algo?
Yo podría, buenos días.
Listo, ya te escuchamos. Ok, excelente. Bueno, ahora te recordar los quizzes en Francia porque los tengo que calificar a mano. No son múltiples opciones, entonces eso en forms no se puede configurar bien. Pero la manera de calificar no es así. Ahora, cada respuesta, o sea, poner o omitir un solito, incorrecto, quita un punto. Entonces, uno puede lograr hasta 2 puntos, pero con cada escrito que no está, que debería estar, o que con cada como que para al revés, que pierde un punto. ¿Sí? Así debe estar. Ok, muy bien. Entonces, ya, no. Sí. Yeah. Okay, very good. No, I'm quite happy that I'm okay again. But also I was happy to have a bit more time because I changed a bit the content of this class. I think it has improved a lot. But let's see. So, so the topic today is, or the goal today is that we understand how we can prepare the data to work in Pytorch. Specifically, they are not nice. Not nice means not numeric, missing values, maybe not even tabular. Okay? So maybe sequential, not all of the objects have the same length, so we have paragraphic sequences. Some maybe like 25 seconds, others a minute or so. So data may be highly not homogeneous, right? Okay, so I didn't think that I would have slides for this class, but actually it turned out that it would be good to have some. But we will also see codes or ideas to cover quite a bunch of things today. I suppose that everybody is already familiar with preprocessing in general and knows how to do preprocessing in the scikit-learn. You know how to impute missing data, you know how to do scaling, you know how to replace categorical attributes by numeric attributes. I suppose that you know all of this already, okay? But today we look how we handle things in Pytorch. Okay, so to understand how things work in Pytorch, I thought it would be best to have a diagram that explains a bit which components we have. So, okay, so I will use my mouse here so everyone can see, also the guys who are online. So maybe as the first recommendation, I really recommend to you that you have a look at this website here. Okay, so I will send the link here. So this is the Pytorch documentation of data. Data sets. This is a very good documentation, but it's also very good that we have some additional content here today. So, but everything that I will explain is also like contained in this documentation, but it's maybe not so easy to understand without additional explanation. Okay, so this is an UML sequence diagram, which I suppose most of you can read or already know this kind of diagram, but even if not, it should be pretty intuitive. So, as you know, in Pytorch, we don't have a fit method or something like that. So we have to do the training, we have to implement the training loop ourselves. So like the starting point, the diagram is to read it from the right to the left, not from the left to the right. So we have some custom code here where we want to train a model, okay? And the question is where does the data for this learning process come from? So you already know that, probably you should already know that in Pytorch you have this data set thing, okay, where you actually access the training instances, but also evaluation instances. And you also have a data loader that provides you with batches of instances, okay? So data set is like what exists, and data loader organizes that what exists into batches, right? So but then we have three additional objects here, and I now want to explain to you what happens internally in Pytorch, because it's really important to understand this, because you can customize almost everything of this. And it's also important to customize this from time to time. So the only thing that you do not customize is the data loader. This is always the same, but the rest you can customize. So in the training, we will say at some point, I now want a new batch of data. Okay, this is our point of entrance now for the discussion. Give me a new batch of data. And this is this point up here. Okay. Okay, and what we do when, I mean, what do we do when we want to have a batch of data? We tell the data loader, give me a next item. This is how it works and how we also did it, I think, in the homework. I'm not completely sure. You have to implement a training loop, I guess. But so the training loop iterates over the data loader, and every call to the data loader generates a new batch. Okay, so this is like this. Actually, it would be maybe better to not. I will replace this. So here we don't call iter, but actually we call next, because we get a next batch from the data loader. Now, as we do this, what happens inside of the data loader? The data loader, and here we are talking about what's called max data set. So the data set is a bit like a table. Okay, so we have a fixed and constant number of instances available. So the data loader will decide which instances go into the next batch. Yeah. So maybe if we have the first round and we have, for example, batch size 16, then you will either take the first 16 instances in our data set, or it will sample random indices. But the data loader doesn't decide this by himself. He uses what's called a sampler. Okay, so the sampler basically decides which instances go into the batch. So the data loader has access to a sampler, and he asks him, give me a number of 16 indices. And the sampler could tell him maybe, okay, the indices are 0, 1, 2, 3, 4, 5 until 15. That would be a sequential sampler. This is implemented in Pytorch. It could also be a uniform sampler that will say your indexes are 4, 17, 91, 63, and so on. Okay, so but you will get back a list of 16. The data loader gets back here a set I of 16 or whatever the batch size is instances. Here, so far. Yeah. Okay, so after this, the data loader knows, okay, I should put the instances with these indices into the batch. Now, where do I get the instances from? Then here at this point, then the data loader accesses the data set, and he will ask the data set, hey, data set, give me the items with indices 3, 17, 91, 63, and so on. Well, the indices that were told to the data loader here. Okay, so this is the set of indices, and then he goes in a loop over these indices and asks the data set for each of these indices, hey, data set, give me this instance. Okay, the data set now can do several things. Maybe in the simplest case, it just has all the instances already stored, maybe in a pandas data frame, for example. So the data set usually is not the table itself, but it just has another pointer to the actual data source. So this data source, this could be, for example, a pandas data frame, okay, or a NumPy array or whatsoever. And the data set then just asks, okay, give me your instance number I. Okay, so this is maybe just a forward logic, but he can do a bit more here, and we will see also in a bit what the data set can do in addition. But then he returns this instance to the data loader, and then the data loader creates a list of 16, or whatever the batch size is, 16 instance objects. We're not at Pytorch tensor level yet. Okay, so this is a Python list that he compiles. But in the end, what we have, and this is why this is written in red here, the requirement that we have is when we want to have a batch that is a Pytorch tensor, because we need tensors. Okay? So how do we get from a list of instances to a tensor? Well, this happens in the collate function. So once the data loader has a list of instances, it will send this list to a function which is called the collate function. And the collate function converts this list of instances into a batch. Now, this sounds a bit complicated. Why do we use such a function? Why does the data loader not just take the list and convert it into a Pytorch tensor? We will see in a bit why this is being done. Okay, because but after all, this would give us more flexibility. But in the simplest case, and there is a default implementation here, which is called the default collate. The default collate will do exactly this. It just takes your list of instances and converts it into a tensor, okay? Into a Pytorch tensor. And then this is being returned, and then the data loader says, okay, now I have a batch in the form of a Pytorch tensor, and this is what I returned here. So all of this happens in each cycle of the inside each epoch, actually. So because what is an epoch? An epoch is that I iterate once over the data loader. This is an epoch. And at every iteration, all of these steps happen. In every iteration of accessing the data loader, all of these steps happen. Under the hood, we don't see it, but it happens. And we will today open this up a bit because this is really important to understand, because in many cases you will want to modify some parts of this process. Okay? Any questions so far?
I was thinking in cases when we are working with parallel computing environments about the indices, because when you work with those environments, indices are not unique. I mean,
You mean these indices here?
yeah,
They should be unique. So the assumption is, so the question is, of course, where parallelism takes place. Here in this scenario, we assume that you have some sort of table. Okay? Or I mean, it doesn't need to be a table. It can be, but like you have a fixed number of training instances available. Like let's say 1,000 instances. And the instance number I is always the same instance. Always, like by definition. So the I here is so to say the unique number of the instance. And even if we use parallelism, this shouldn't change. Yeah.
that means that Pytorch do some mapping of the entire data set before he starts.
You can think of the data set as a map. This is why it's called the map style data set, where the index is the name of the instance, so to say. There is a different type of data set that we will see in the end, but this is, by default, this is the way how you think of it. And then there is really not really parallelism at this point here. Actually, all of this also happens on the CPU. So even if you do GPU-based training, GPU doesn't come into play here at this point. All of this is running on the CPU. GPU, so once you receive this guy, then you can move. So once you have the batch tensor here, you can move it to the GPU and do the forward pass. But there are some sophisticated techniques which are not necessary for everybody, so I will not cover it here, but you can do some sort of parallelization in this data loading process to make sure that as soon as the model is ready, it can already take the next data, because we don't, we definitely don't want to this here to be a bottleneck, because typically the model is the bottleneck because it's slow. This should be fast, generally. So sometimes this here is parallelized, but this will not change anything in the general logic and also not in the indexing. Okay, good. Other questions?
The sampler, what are the rules that we can use to define how the sampling works?
Very good question. So here in the documentation, you see here. So there is a section about the samplers, and there are different default choices. So there is a sequence. So here, for example, you see there is a sequential sampler. So it's not like so there is a sequential sampler, there is a random sampler, there's a subset random sampler, a weighted random sampler. So these are all already predefined. And then you can basically, so when you are a batch sampler, so what you would do would to create a new object of this and pass it as an argument to the data loader. So when you create the data loader, you can tell it, this is the sampler I want to use. And by default, it's the random sampler that will just pick random instances from the data set.
Then when you config the parameters, you can use more about one or only one.
Only one or
For example, a random sequential, or you can have the possibility to change the parameter.
inside a single data loader, you only load one. Okay? You only have one. But if you want to do crazy things for whichever reason, well, I mean, in the training loop, you can just say after like 3 rounds, so, oh, I want to change my data loader. And use a new data loader with a different sampler. I mean, it would stop you. Yeah. And it's exactly this kind of flexibility that people want to have, and this is why Pytorch doesn't offer just out-of-the-box things, but it offers a really great out-of-the-box process. And I think you can, I mean, whatever you want to do, you will be able to do with this here. Good, okay. Now, there is no such thing like imputation or replacing categorical values in Python. There are no such things implemented. So we cannot just like say, yeah, in Python we have the simple improvement, and the k-nearest neighbors improvement. We have something like that also in Python. We do not. Doesn't exist. Okay. So the framework. So there is some logic for pre-processing, but this is really specific logic for image pre-processing or audio pre-processing. So these kind of things are implemented, but not like for that tabular data. So what we typically understand by pre-processing data. Okay.
Yep. Short question. Which of the elements, either the sampler or the data loader, is the one that has the responsibility of not choosing an index that was used in before?
The data loader.
The data loader.
The data loader,
Okay.
or the sampler.
Yes. Question is like the answer is which one of those do the thing?
The sampler.
The sampler. Okay.
Yeah, the sampler. Okay, so one thing I didn't mention is that the sampler, in order to do its job, it needs to know how many instances exist, right? So because I mean, the sampler must return an index, but if we don't tell it how many instances exist, then it maybe says, yeah, index 3050, but we only have 1000 instances, so it doesn't work, right? So the data loader tells the sampler how many instances exist, and then the sampler is responsible for making sure that you don't have repetitions, or also to allow it if for some reason you want to allow repetitions within one go. Okay. Good. So also there is no such thing like training and validation data in Pytorch. I mean, we can do this. We can create training and validation data, but and we can also create all other sorts of data we want. But there is no such thing like train test split, like in scikit-learn. So they just say, you know, there is data. There are ways to access data. We give you a general framework to do this, but everything else you have to do on your own. So if we want to split data into training and validation data, well, we have to do this offline, so to say, before. And these will just, I mean, inside of Pytorch, these will be just two data sets. Yeah, and they will follow exactly this scheme. So there is no such difference. Okay, so the slides really are a bit just kind of documentation, so that you have something left after the class, not only what I said. So, okay. Now, what is interesting, and we get go back to the slide, is that since the data set class here, this is really a class, and we can inside this class we can implement logic. So this data set is really more than pandas data frame. A pandas data frame, okay, it has also logic, but let's say a CSV file. I mean, it's more like just the data, but we can do and manipulate the data even on the fly. And actually, we will want to do this. So, for example, data augmentation. Data augmentation means that I want to create new instances of my data, maybe with a predefined label, to enhance the basis for learning. And this data augmentation would take place here. Okay, the data set can do this itself. And I will show you an example how this works. Okay. So here we can also implement exactly. So here we can also implement logic, but data augmentation, for example, is a logic we only want to apply for training data, not for test data. Okay, sometimes you can also apply for test data, but typically it's not done. Okay, so we should probably in some cases make the difference between training data set and evaluation data set in some sense, but this is something that we must do. We must design the data set so that maybe data augmentation is enabled for one object on this data set, but it's disabled for another one. So we can, if we create our custom class, our own class for training, we can give it a flag that says augmentation enabled, and this is set true for training, and it's set to false for a validation, for example. I will show you how to do this in a bit, but before we go into more technical depth, so how is this connection between the data loader and the collate function? So the data loader really, the data loader calls the collate function. That was this here, right? So I'm now talking about this part here. So I'm explaining how this works. So the data loader really calls the collate function with the list of the instances. The collate function returns a batch tensor, and then the data loader doesn't look at it anymore. It really just forwards this tensor. So that will also mean that if at the end you want a batch tensor, then this collate function must make sure that it really delivers a batch tensor in the desired. Okay, so this is something that we, and in particular, then what this needs to return is some sort of structure of tensors. So what is really important to understand here is that this is not anymore like I have X and Y, but maybe I just have an X. So in deep learning, I also can learn without labels, for example. Okay, so maybe I just have an X. Maybe I have X, Y, and Z. So maybe I have three things. So it's not like in the scikit-learn where you have X and Y and you do a train test split or you batch something together and it's always X and Y. So what do we know? Actually, what we will always have. So the only thing that you know that you will always have at the end of this figure, so what you have here, is some structure that will contain tensors. This is all you know. This is everything that, okay, like this is all that is agreed upon by contract. Everything else is free. So maybe this could be a single batch tensor, but it could be also two tensors, one for the X and one for the labels. But it could be also 3 or 4. But typically, I mean, you have a number of tensors and all of them have the same length because it's the batch size that defines the length. It could also be a dictionary, for example. Okay, so so there is no general notion on this, how it should be done. I will show you an example where we have this structure here, which is like maybe the most common one, where you have a couple of 2 entries, and inputs is a Pytorch tensor, and targets is also a Pytorch tensor. Okay, but you can basically do whatever you want here. Only in the end, your training loop receives this object and must understand what it gets, so that it can do something. Okay. So,
quick question.
Yeah.
On the diagram, wondering why are you using orange for the batch tensor that is going back to the training loop, and the batch tensor that you are sending to the data loader is in black? Is it some kind of notation?
This here?
Yeah.
This here? Okay. I mean, no. Actually, this here is exactly the same as this here. I just made it red here because I wanted to say that here we have a kind of requirement definition, because as soon as we have an object here, what we want is that we talk about Pytorch tensors. At any point between this here, we can have different objects. We can even have at all points here, we can have NumPy objects, for example. No problem. Maybe we have tensors already at this point, maybe not. But the only thing that we know for sure is that at the end of the process, we need Pytorch tensors. Whether we have them in the middle already, that's a different question. So this is why I made it in red, only for this reason, because here from this, or this edge comes with a requirement definition that what has to go out here must be a structure of tensors. But this implicitly also means that what goes out here also must be the same structure of tensors. So it could also be put in red, but that was like to say, here we have a requirement entering the equation.
But actually,
Got it. Thank you.
it's, I mean, in the diagram, I understand something, maybe I am wrong, but data loader is actually whom has the possibility of collect the data.
And
So when you go to collate the function, collate function sends just like the structure of the batch sensor, but not the batch sensor itself.
no, when I'm saying structure of tensors, this means it is tensors. But it's not only one, but it's like two. So if you want to think of this like X and Y, like in the classical case, then what this returns is a tuple X, Y, and X is a tensor and Y is also a tensor. So when I say structure of tensors, I don't mean just description of how in general these guys look like, but yeah, it's the concrete tensor, but it's not only one. It can be several. Yeah. So data loader is really, I think it's best to think of the data loader as a kind of manager. This guy doesn't do anything by himself. He just organizes this whole flow. He asks the sampler to get an idea of which instances go in. It asks the data set to it tells the data, asks the data set to get the concrete instances, and it asks Collate to put them together into a batch.
Okay.
Into batches that, he already creates the batch at the list level, but Collate turns this batch at list level into a batch at tensor level. It would be certainly good to see an example. I just wanted to say that there is a convention that in the tensors that you receive, the first dimension is the batch size, right? Because so these guys here, every instance has a dimensionality. Maybe it's just a vector, but maybe an instance itself is also a matrix, or even a tensor itself. So if you have a 3D, an RGB image, for example, then a single instance is already a 3D tensor, because you have width, height, and color. Okay, and so what Collate basically does is it takes several such tensors and puts them together into one tensor that is then 4-dimensional. And where is the batch size, or where is the batch dimension in this 4D? Well, it's the first one. So the first dimension is by convention the batch. Okay, so with the first index, you address the instance inside the batch. Okay, and the other dimensions, well, you can have whatever you want. They just must match what your model.forward expects. So your model, as all of you have implemented first neural network in Pytorch in the homework. So you have a forward method that receives an X. For this X, you expect some shape by construction of your network. Maybe this X is just a vector, but maybe it's a 3D tensor because it describes a 3D RGB image. Yeah. So you can have whatever you want, but what these other dimensions here, the remaining dimensions must match what your model expects. Okay. And what is interesting is that these values in the tensors also may contain non-values. Okay. They may contain non-values, missing values, but it may not contain strings, for example. So if you have a NumPy array, in a NumPy array you can have strings, but in a Pytorch tensor you cannot have strings or other types of objects. It must be numeric. So this is an important difference here between Pytorch and NumPy. You will get an exception if you try to put a string into a Pytorch tensor. Okay, so you can have none, but you cannot have categorical values. Now, what happens if we have non-values? So if we have non-values, non-values will, like any operation mathematically that is defined in Pytorch will evaluate to none if one of the inputs is none. Okay. So we will not get an exception if we work with non-values, but it will just probably fail silent. So here is an example. See it here, and so this is super simple. We import Torch, okay, and then here I define a tensor. That's like this is a 1 by 3 tensor. Okay, so it's a single instance with 3 entries, and it has values 1, none, and 2. So if I replace this guy here by a 3, for example, then I can apply a linear layer. So here I have a linear layer in Pytorch that has 3 input neurons, so to say, which makes sense because my instance has 3 attributes, and it outputs 2 output neurons in this linear layer. So here I get always different values because I instantiate this every time from scratch, and the weights are instantiated every time from scratch. Well, but that's not so important here. But the important point is if I now have a none inside of this, then everything will become none in the output. But there's no exception. So this is also very different from scikit-learn. In scikit-learn, I would already have the destroyed model now because we get an exception, but here it just forwards the none. And eventually what will probably happen is that everything is going to be none. See? So at the end of the network, if I do my forward pass, probably what comes out will be none. If I have one none in the input. Okay. So technically it's possible, but most probably we want to avoid to have non-values. Okay, so we want to do imputation of the values unless you have a network that is specifically designed to treat non-values for some reason. Maybe you have your own custom layers in the network that are able to treat the non-values. So, I mean, you could write your own Pytorch module where you treat non-values somehow, okay? And then that's perfectly fine. So it's just important to understand how this works, right? Yeah, okay, so I said this already. Yeah. So what is the most likely case that will happen if you have non-values? Yeah. So the most likely consequence of you having non-values is that your model will output non-values, and then you compare in your loss function non-values with ground truth, and then your loss will also be none, and then you will probably have a crash somewhere. I mean, you can still compute this, but then if you do the back propagate, you will probably have a crash at that point. Actually, I didn't try this, but I suppose that you cannot do a back propagate anymore, a backward, if you have nuns. Okay, I said this already. Okay, so then yeah, how would we then, so here we understand that we want to have preprocessing. I mean, we have missing values, we want to replace missing values in a reasonable way. We have categorical values, we need to replace them because Pytorch cannot handle string values, for example. So how would we do it then? If Pytorch doesn't come with its own methods for that, well, I mean, how would you do it? How would you do pre-processing if Pytorch doesn't operate? What would be the simplest solution, maybe?
To create a random orientation of the different categories. And although they are random, the process of learning is going to.
I mean, okay, so you're more like speaking conceptually, like I'm saying you already know how to do it. You want to do a one-hot encoding of the categorical attributes, and you want to do a mean imputation, for example, for missing values. You know that. So how would you do it concretely?
Basically using scikit-learn.
Right? Yeah, exactly. So if possible, that would be the first strategy. So no, strategy one would be, we're talking about 4 possible preprocessing or loading strategies now. In Pytorch, first strategy, and even the preferred choice, don't do it in Pytorch. Do it inside of Python. And NumPy, pandas, and whatever you want. And then, you do all the pre-processing you want with a pipeline, scikit-learn pipeline, in the well-established way, how I taught you in ML1, that you fit on the training data and you transform on the validation data. So you do not use all of your data for doing the pre-processing, but you do a train validation split at the scikit-learn level. You fit your pre-processing pipeline only on the training data, and then you transform them, and then you also transform the validation data. And then at the end of this process, you convert this output into Pytorch tensors, load them in Pytorch, and then you proceed in Pytorch without missing values, without categorical attributes, and so on. Okay, so let's do it. So here I load now all sorts of stuff that we know from scikit-learn and from pandas and so on. So I load the eucalyptus data set. This is a data set that everybody of you who has seen a class with me before knows already. It is a, I think, 5-class classification data set. Importantly, it has missing data and it has categorical attributes. This is why I always use it, because it's such nice. Okay. So here I only load the data set and we report the shape. We go down here, so we see the shape is we have 360 instances in total, 20 attributes. And we see here categorical attributes. I don't see missing values here in this overview, but well, they are there, believe me. Okay, good. Now, then we split the data into X and Y, because we have a supervised learning problem here. So utility is the name of the class column. So we drop it, and for X we drop it, and for Y we keep it. And then we do the training validation split at this level. Okay. Now at this level we couldn't input any of this into Pytorch, because I mean, even if we convert it, we couldn't even convert it to tensors at this point, because there are categorical values, right? So here I just have a flag to enable or disable the pre-processing. But what I do here first is I do quick scan which of the features are numeric and which are categorical. This is a really bad practice. You should not do this like this, Because what I here do is that I say the numerical features are those that have numbers as the values, and the categorical attributes are the others. Well, the second is okay. So you know that if an attribute is categorical or has string values, it must be categorical. But the point is, you don't know, or you cannot conclude that only because you only have numeric values for a feature that it is a numeric feature. So maybe categories are named 1, 2, 3. But this is not a number, it's a category, okay? So this is why it's really a bad practice. But so in general, you would just put a complete list of the names of the features here, and you know which of these features are numeric and which are categorical. Okay, so this is only here for the sake of an example.
And also because it demands a lot of memory to try to infer a type.
Yeah, but here it's only based. Here it's only inferred based on the column type. So this is super fast here, but yeah, if you want to do more sophisticated things, then depends on the data set size. So if you have a really huge data set, then this can be, yeah, also very expensive. Okay, so then we define our pre-processing steps. All of you who have seen ML1 with me have done this before. We have a simple imputer, we have a scalar here. For the numerical guys, for the categorical guys, we have also an imputer, but with a different strategy. Here we use the mode, like the most frequent category. We have a one-hot encoding, and these are put into a column transformer, and then at the end we can use these pre-processing steps to convert our data. So we take the preprocessor, do the fit transform on the training, only on the training data, and then we do the transform on the validation data as we learn it. Okay? So now we have xtrain and xval. At this point, these will be NumPy arrays, no matter what they were before. If they were data frames before, if they were, doesn't matter what they were before, but now they are NumPy arrays at this end, because scikit-learn will always output NumPy arrays at the end of this process, okay? For the same reason, I'm not, okay, so this line actually is not necessary only if one doesn't have this preprocessing, so forget this line. And now we want to go to Pytorch, right? Now we have data that doesn't have missing values anymore and that doesn't have categorical values anymore. So let's go and move it to Pytorch.
Before you continue, what's the difference between fit transform and only transform for the xtrain and xval?
Here,
yeah.
Fit transform is just a shortcut for fit and then call the transform. Yeah, I mean, so so we can have a quick recap of the ML1 class. So here we talk about preprocessing now, and here. So when you create your preprocessing pipeline, you want to make sure that you do not, that the validation data does not influence the preprocessor. So if you have a min-max scalar, you don't want that the minimum, the maximum in your data is influenced by validation data, only by the training data, right? So this is why you would call the fit method only on the training data. Mm. But of course, you also want to transform the training data. So with the training data, you want to first build your preprocessors, and then you want to transform the training data with respect to this preprocessor step. With the validation data, you only want to transform. Yeah, and this is why here, I mean, you could also do, optionally, you could do this here. So that would be like to do it in 2 steps. You first do just a fit, and then you do this. That would be the same. Excellent. Yeah, so I'm going really quickly over this because, I mean, this is somehow we already know about this, but of course, if anybody has concrete questions, we can, of course, and we will take the time to solve these. Okay, then so let me quickly show you what are the labels here in this data set. So let's look at this. Oh, I think I have to reload. No, this is not here. So let's see what happens. Look, the value of the class attribute is this here. This is a string. Okay. So the class is good, best, low, average, and so on. Okay. So we cannot use this in Pytorch. In scikit-learn we can. Scikit-learn can cope with categorical target variable, but Pytorch cannot, because Pytorch is only tensors, and tensors do not have categorical values. So we must convert this categorical attribute also into numbers. And in scikit-learn, you do this with the label encoder. So here. Okay, so we now have xtrain and ytrain and xval and yval, and inside of x, I don't have any missing values anymore, and also no categorical values. Okay, but y, the target values are still categorical, and to change this, I create a label encoder and apply this fit transform on it. And what this basically does, it converts good to 4. Average to 3, low to 1, in this sense. Okay, so it replaces all the labels with integer numbers. 1 to k, where k is the number of labels that exist. So here it's, or I think it's, I'm not sure right now whether it's 0 to 4 or 1 to 5, but integers. Okay. And again, I have to do this on the training data and on the validation. But here I use the fit only on the training, and on the validation I only use the transform. I mean, here it shouldn't make much of a difference. What could happen that in the validation data, I have maybe instances that did not occur in the training data. That would be problem, right? Okay, but such a case needs to be treated apart. And now I'm good. Now I have xtrain, x validation, ytrain, y validation. All of them are NumPy arrays without categorical values, without missing values. Everything is numeric. And at this point, I can now make the transition to Pytorch and create now 4 new objects, which are these xtrain t, ytrain t, xval t, yval t. So the underscore t indicates this is a tensor. Yeah. So this underscore, this suffix here, this indicates that we have a tensor. And I use torch.tensor to convert the NumPy array into the respective Pytorch tensor.
There's some specific reason to use float 32 for x and lump for j.
Yeah, absolutely. And actually, this is very important. We saw it already in deep learning in the first course. So for the labels, you need long. They must be integers. Otherwise, you will have problems in the computation of the loss. So remember that torch is not as nice as NumPy. In NumPy, you can almost do whatever you want. It's really like crazy what you can do in NumPy. You can compare booleans with floats, and you will not get an exception at all. You will. So a lot of things work in NumPy. Those things will not work in Pytorch. So why is that? Is it because in Pytorch they didn't make the effort to make it usable like NumPy? No. It's like they say in Python we want to be super efficient because deep learning is slow. So a lot of operations, and we cannot afford that incompetent people use it in a way that is not like optimized. So we don't want to lose or waste time by converting types to make them compatible. And it's really the task of the user to make sure the types are working in the way how they are expected. So this is why in Torch you will often get exceptions that some types don't match. And you would not get these exceptions in NumPy because NumPy just converts it for you and you're done. And in Torch they say this is not the way how we operate. In Torch everything must come as it's expected because we want to optimize performance. And converting types is going against performance. Now, float 32 is the standard data type used by the layers in Python. This is a bit strange. I have not understood yet why it's working like this, but if you do not specify this here, so if you would omit it, then you would create a float 64 tensor. And float 64 is not compatible with float 32, and you will get an exception if you pass that into your model. So I don't know why at this tensor level here, 64 is standard, but in the linear layer or in the layers of Pytorch, 32 is the standard. I don't know why they have done it like this. Probably it will change in a moment, but or at some point of time. But yeah, okay. For now, it's good to know that this
Maybe some backward compatibility with hardware.
could be. I'm not sure about this. Okay, and now we have Torch tensors, and now we must make the step. Oh, sorry, that's not the slide.
So sorry.
Yeah.
Because the long format for the target, but what happens if you are going to train a regressor that?
Yeah, then you don't have this issue. Okay, no. Wait, so, okay, good point. So, why did I say that you have to pass this to alone? I mean, when
In this case,
you will use this only when you compute the loss function. Because in the forward, so what do you give to the model? To the model, you only give the X train, right? So, I mean, we can also look down here. So here we get the batch of X's and Y's, okay? So where do we use the Y's? Only in the computation of the loss, which is here, okay? Now, if your loss is a regression loss, then you can have numbers that are floats. But the point is that if we have our criterion here is, as you see, the first line is cross-entropy loss. And for cross-entropy loss, the ground truth must be long. So for regression, you don't have a problem. Then you use also float 32 or float 64. I am not sure, depends. Well, you have to check in the documentation which one it is. I'm not sure by now. But then you don't have a problem. Yeah. But then you wouldn't use long. So long is really only here for the. So we're now here at this point that we have the data source ready, not the data set, the data source. The data source are now 4 tensors: X train, Y train, X val, Y val, Pytorch tensors. Okay, now we are creating this guy here. Yeah, and this guy, well, we can create manual subclasses for this, but there is also a standard class if we already come with Pytorch tensors. So if we already have Pytorch tensors, we can use a standard class from Pytorch, which is called the tensor dataset. Okay? So in the tensor, what does the tensor dataset receive in the constructor? Well, it receives a list of tensors. It could be just one tensor, it can be two tensors, like here. It can be three tensors or four tensors, doesn't matter. Okay? So it receives a sequence or a list of tensors. So here we tell it, my first dataset consists of two tensors, X train and Y train. And the validation data set is also a tensor data set that consists of. Okay, so here again we bring them together. So now we have two objects, two data sets, a train data set and a validation data set. So we have two objects of this here. Yeah? And accordingly, we create two loaders to manage these guys. Okay, and we tell it batch size 32. And here we also configure the train loader to shuffle. Okay, so we have two data sets and with two data loaders. And each data loader has a sampler and a collate function, only that we didn't specify it. Yeah, it's implicit here. Good. And now at the end here, we can go, for example, over the train loader. And this here will, so every iteration of this loop here will do this whole process that we have here. Okay. So going once in the loop will do this process. Going the second time in the loop will do the process again, and so on. So here I'm doing it just once, and then I break the loop. And so I have a lot of stuff going on here. So maybe I created a separate cell for this. Here we have. This is something I really think about. Really. Okay, so here we have the batch, and you can see that it curves. So we see we have a 32 by 90 batch. Why is it 90? 32 is clear because that is the batch size. But why is it 90 if my original data had what? 20 attributes.
Because we were using one hot encoding.
Exactly. Because we did a one-hot encoding, and then here at the end, you can also see that the shape at the end for training validation already has these 90 columns. Okay, so this comes from the pre-processing precisely, right? Okay. And by the way, because my data loader is shuffling, I get a different batch every time I run this loop. So here's now something interesting happening. Here I have an X batch in XB and in YB. So why do I have two objects here and not only one object or three? But this is exactly coming from the definition of the data set. So let me collapse this here. So in the data set, we said, well, I have a tensor data set that consists of two tensors. Okay. So what would happen if I put a third tensor? Let's say I repeat the training tensor, the X train 2 times. I mean, it doesn't make sense, but let's just do it. Okay, so I can run this guy. Okay, and now here I will get an exception because he will say I'm expecting 2 objects here, but he gave me 3. Yeah. So here I could now have like XB2. Okay, so do you see this flexibility? So I can do whatever I want in my data set. I can say it consists of like 3 objects, like for every instance, I have like 3 things or 2 things or just one thing, doesn't matter. Only at the point of time in the training loop where I want to use it, and then I have to know whether it's 2 or 3 or what's going on here, okay? And this is the reason, so I need to understand how I configured my data set to understand how I need to extract things from the data loader. Okay, well then let's use a neural network now to train something on a data set that originally had categorical attributes and also missing values. So we will define a simple neural network here with two linear layers. The last one is just the output layer. So it's two hidden layers and the output layer. Here is something, not sure whether everybody already used this. You should definitely know how what this is and how it works. So there is a huge number of functions that you want to use in deep learning. So of course you want to use different activation functions. And you want, but there are also other functions. So Pytorch has really a very huge file. I think it has like 5,000 lines or something, which is this file here, the torch nn.functional. In this file, they have all the functions that are used ever inside of Pytorch. Okay, like mathematical functions. And now, if you want to use a ReLU or an activation function, you could, in principle, put a layer inside here, but this is not considered in practice. It's considered better in practice to only, because this ReLU function doesn't have a parameter that is being learned, okay? So it's better to just call the function in the forward. So when you want to do a computation, just do it like this here. Oh, so you should here in the constructor, you should only have the layers that have parameters that you want to learn, that are stateful for some reason. Okay, so only if you have things that change during training should be defined up here. Everything that is only a function that is always behaving in the same way should be called over this so-called functional API. Yeah. So here, what I do is basically I import this file and name it F, capital F. And now I can use every function from this file with a dot notation. So here, the network puts my input into the first hidden layer, then it applies the ReLU to it. Then this output is put into the second hidden layer, linear layer, and I apply the ReLU to it. And at the end, I apply the linear layer in the output to the signal. And I output, importantly, I do not output probabilities. I do not have a softmax here. We don't do this in Pytorch. We only output the logits for the 5 classes, and then the loss is computed on the logits. Right? Okay, so then we create an instance of this model here with the respective input and output dimension. I say how many hidden like how many neurons do they want to have in the hidden layer. Okay, and then we start training. So we use cross-entropy load, we use Adam, we tell Adam about the parameters, and then here I have a definition. So I'm not starting training here, I'm defining the training process. And training means that I first enable the train property on the model. This is important because there are some things that I have some components in my network that should not be applied if I am not training. So for example, I have a dropout layer. The dropout layer will erase certain connections randomly during the forward pass. But I don't only want these dropout units to be applied if I am in the training mode. If I'm really making predictions, in reality, I don't want dropout to be used. And how do I tell the model that it should not use dropout? Well, I'm telling it to go into the eval mode, which is this here. And if I do this, then my dropout connections and others that are only to be used during training will not be used. My network doesn't have dropout. I'm just saying, okay? Okay, so here I go over the data loader. Each run in the data loader is going to be one epoch. So this here is one epoch. It's also why it's called train one epoch. Okay, and in this during this epoch, at the beginning of each batch, not at the beginning of the epoch, that was one question in the quiz. So one error in the code in the quiz was that this guy here was used outside of the loop, and that is wrong because then you aggregate all the gradients inside along the batches. Okay, so this zero grad must be inside of this loop. Then we do the forward class, get the outputs of the network, we compute the loss function, and we do a back propagation step. And then once we have the back propagation step, the back propagation, what does it do? It fills the gradient values for all the variables, right? And then we can tell the optimizer, now you can adjust the weights. This step was also missing in the code, right? So this, I mean, without this, we don't learn anything. We only do a lot of compute, but we don't do anything else. Okay, then we have some computation here. I don't want to go into the depths of this, but in the end, then I apply these two guys. We train something, and we see that the training loss goes down, validation loss also goes down. And I also put this into a figure where we see on the left the loss, like the cross entropy value, and on the right the accuracy. What you can see is a super nice example of overfitting, because the training loss goes down all the time, okay, forever basically, and the accuracy goes up and converges to 1. But what you can see after only like 10 epochs is that the validation loss, well, it also drops in the beginning, but then it goes up again. Okay, so here this is a really, really bad situation. You can also see it here in the logs. So after, so validation loss goes down until here, epoch 12, but then it goes up, and it goes up and goes up, and it even becomes worse than in the beginning. Okay, so very nice example to illustrate why we need validation data to stop the process of learning early. Okay, very nice. So far, so good. So here we were. That's the easiest way to do things. Okay, so this works well if my data is tabular. If data is small or medium sized. What does this mean? This means that if you load it into your memory, it will not use more than, well, at most 30% of your memory, hopefully. Better is less, because your model will also consume memory, so the data shouldn't exhaust all of it. And if we don't want to use data augmentation, because data augmentation means, I want to, for example, I want to make some changes in the data, but I want to every time different changes. So I cannot do data augmentation in this offline phase. So data augmentation and pre-processing, offline pre-processing doesn't very well work together. Okay, so second strategy, we can create our own class for data set. So going back in the figure, what this means is I can create my own data set. So currently we are using this tensor data set from Pytorch, but we can create our own data set. And if we create our own data set, for example, because we want to do data augmentation, then we can inside the data set say what we want to do. So here's an example. No, this guy not. So this guy. So I want to create data set for MNIST. MNIST, we all know MNIST, the handwritten digits. Okay, very nice. So what I do here is I subclass the data set class from Pytorch, and I create my own class. If I subclass dataset, I need to implement two methods. The len, this is so that the data loader knows, okay, your dataset has so and so many instances, then I'm going to tell the sampler there are 800 instances in your data. Okay, this is why we have to do this. And the get item. The get item is so that we can call this here. Yeah, so that the data loader can acquire complete instances. Okay, and what we simply do here is that we load the data set in the beginning. So when I create a new object here, I download the data set MNIST from the server. And then And then in the get item, in the in the len, I simply return the length of the data set, so I don't change anything about this. So base data set here, I have this, it's like still files. And then for a concrete index and get item, I will get the image and the label associated with this instance. Okay, and I return this. The only thing is now, and here we have the magic, because up to here it's just a data set, nothing happens. But now I can say I will augment the images. That means here I have the original image from the data set, from the database, and now I want to do a modification. I want to do a rotation, or I want to cut something out, or so. Doesn't matter. Then I have my own method here, augment, that is defined up here, that we can see in a second what is going on there. But it's basically like this. This here is taking the image and it changes a bit. But I mean, if we rotate a 7 a bit, it's still a 7. If we crop out something of a 5, it's still a 5. So we don't change the label, only the image. Okay? And then we return it. Now, what is the important point here? That we are now doing 10 different epochs. Okay? And in every epoch, we will decide randomly whether we will, for a specific instance, like the first image in the data, we decide whether or not some of these techniques are being used, and if they are used, they are applied randomly in a different fashion. That means the same original image will have different augmentation, not always the same augmentation. Here. So if I originally have 10,000 images, what I basically get here is now a stream of instances, an infinite stream of instances that all will be different. Because every data augmentation is a bit different than the other. Okay? And I could not do this if I would do it in Pytorch, in scikit-learn. Let alone that in scikit-learn it's not possible to do this kind of nice transformations on image because it's only tabular data. And now we have an example where our data is not tabular. Okay, so for example, here I do a rotation of 20 degrees of an image, but only with a certain probability. It's not done always, only sometimes. Okay, and then also the color is a bit changed here. And in the end, this image, so these transforms, these are like pre-processing techniques for images that are pre-implemented in Torch. But this is on images, okay? And it's not like something like imputation. At the end, so this here is like a chain of different pre-processing steps or augmentation steps I want to use. It's a bit like this sequential to define a model, but now it's a sequential to define transformations. And in the end, I convert the image to a tensor because I need a tensor, right? So here is a simple dataset definition with 25 lines, but this is infinitely more than what I could do with scikit-learn. Because in scikit-learn, I create a fixed dataset and it will be always the same. Every epoch gives me the same instances. And with this here, every epoch gives me different instances because the instances are being changed on the fly. They are changed on the fly. So I change it here, I return it. So basically, inside of this edge here, I do a transformation of the original instance. Here I have the original instance, the original number, and here I do a transformation, I return a transformed instance. This is pretty cool, and I show you an example here. So we run, we create like 5 times the same batch. The first, what? The first 8 numbers. Okay? In the first, I don't apply augmentation, but then I create 4 new batches where I do apply augmentation. Let's see what happens. So, yeah. So here I create every time a new version of this. Okay. And dare to, no, I cannot really explain this currently because I closed it before. But okay, so I have a data loader with this data set, batch size 8, and now give me 1 batch. This here gives me just one batch, the first one, and then I plot the figures so that we can see what happened, okay? So the original figures are these. This is the original batch. And the first 8 instances, a 5, a 0, a 4, a 1, a 9, a 2, and so on. But then look at this next one, next guy. Well, this looks pretty much like the one above as well, but look at this. This is clearly different than this. This 4 is also different than this one, this 4. This one is also different. It has a different angle. Do you see this? I mean, this is almost a straight one, vertical, and this is not vertical. So we see, and here we see the same. This 3 has also been rotated, so you can see that we have modified images. Now the gag is, if you go now to the next epoch, then the same instances will have different modifications. Now look at this 5, and look at this 4, and look at this 1. This one is again more closely related to the original one. So you see that the modification is different in every epoch. And this basically means that you have almost a stream of instances. You have a finite pool of original instances, but you can create as many new instances here as you want. So we are running a bit out of time. I want to show you also another example, but let me move on a bit. So, but this is the oops. Okay, so this would be this the second strategy. Okay, so if we cannot use scikit learn because we want to do data augmentation, or because our data is unstructured, like images, it's not nice to do pre-processing on images in scikit learn. Okay, so then this should be a good option if the data set is still small. Third option is we can customize the collate function. Okay, so the data loader retrieves a list of samples from the data set and collate ensembles this list into a batch. So we can use this logic to say, I'm doing, for example, a different type of data augmentation in collate. So for example, there is data augmentation where I take 2 images and I put them together into a new one. Well, this is not so feasible in the previous logic because then I have only instance-wise data augmentation. Okay, so I want to show you an example where we have a custom collate function, which is here. So, okay, but this is a slightly different example now because it's not with images anymore, but with numbers. Okay. So here in this case, I load the iris dataset, simply the iris dataset, and I have a NumPy subclass of the dataset class. So here, the only thing that I do is that I memorize the x and the y. The length is the length of x, and I always return the items of the respective item. So this is a super stupid wrapper. What is important here for me that you notice is that this is NumPy. Everything here is NumPy. So this guy here returns NumPy instances, okay? So one could expect that in the figure, oops, here, that this should already be Pytorch. And typically, and if you use the standard, the default collate, this must already be Pytorch because this guy doesn't touch the instances anymore by default. But if our collate function touches the instances and does something with the instances, which is completely allowed, why not? Then we can even here return something that is not Python, like a NumPy array. So this guy here stores a NumPy array and it returns NumPy vectors. Okay, so this would not be compatible yet with Pytorch at that point. But now I create my custom collate function. The collate function receives this batch. This is basically it. This is what it receives. The rest is something I put here, and it's not really so relevant. And what it does that now the collate function transforms the NumPy arrays into tensors. The collate function does it. And then I mix instance a bit together. So I take random instances. I take two, always pairs of two randomly chosen instances, and I mix their values a bit together. Okay, and not only their x values, but also their y values. So we have a one-hot encoding here for the labels, and then this one-hot encoding is mixed a bit together. So before you have a setosa and you have a virginica, and after that you have an instance that is a bit of setosa and a bit of virginica. Sounds strange, okay, but this is a common practice in data augmentation. So if I apply this, so I apply this now, okay. I used it with, above I loaded iris, but here I don't even apply with iris, but just random stuff. So I apply once the logic without the data with the collate function. So here in the data loader, I don't do anything special, but here in the data loader, I tell him, hey, the collate function that you should use is the one I gave you up there. Okay, so here I customize the collate function. And then look what happens. So if I don't do it, then here I have a batch size of 4 only. So batch size is only 4. So these are my 4 first instances. The x's, 5 attributes for each of them, and the 4 labels. Okay. If I use now my collate function, then in my collate function first makes a check. What is it that the data loader gives me? So here you can really see that what the data loader gives to the collate function is a list of instances. And then I'm asking, and what's the first element in the list? The first element in the list is a tuple. Why? Because it's the x value and the y value of the first instance. Okay, so batch is a list. The first element in this list is a tuple, x and y of the first element. And then if I access this guy here, this is so to say the x in the first instance, this is then a 10. Sorry, in my case, it's a NumPy array because it came as a NumPy array originally, right? So here you see it's a NumPy array. And now I apply this, mixing logic to bring instances together, and you can see that the x values are different. So here, this is my first instance if I don't do the data augmentation. Here is my first instance if I do the data augmentation. And what is curious is that you see that also the labels have been mixed up. Okay, so now this instance is not purely label number 1, but it's partly label number 1 and partly label number 2. Okay. Okay, why is this important here? Because I can do now data augmentation at 2 points in process. In the data set, so in Pytorch, I can do the data augmentation either here, but then it's usually only instance-wise. I take the instance and I modify it a bit. I add some noise or whatsoever. But I can also do the data augmentation here. And then I have access at the same time to all the instances in the batch. And I can say, in this batch, I have these 30 figures. Then I combine the third one with the 8th one somehow. Yeah. So this, I mean, in theory, you can also do it here if you access randomly other elements from the data source, but maybe it's not so clean. Okay. Good. And now you also have seen an example of how you can customize your own collate function, which is important. Final remarks. So that was the third strategy. First strategy, use scikit-learn and do this whenever you can. And if you don't want, so if you don't have structured data, tabular data, small data, and you don't want to use data augmentation, which is usually the case, it's not so common to use data augmentation for tabular data, use scikit-learn. If you have unstructured data like images, or you want to do data augmentation, but its data set is still small or medium, use data set, you could create a custom data set, or use the collate function, depending. Collate function only if you want to do a data augmentation that requires several instances. Otherwise, you probably don't need it. Okay. Okay. Sorry. Yeah, that was a bit too quick. Actually, sometimes you need it, specifically if your instances have different lengths. So that's not the case necessarily for images, but could happen. So, for example, your images have different sizes. Okay. Well, for the network, you need them to have the same size. Funnily, they only need to be the same size inside a batch. So you need to resize all of the images in the batch, maybe to the smallest size. Okay. So maybe if you have the smallest one is 28 by 28 pixels, then you put all of them to 28 to 28 pixels. But could be that in another batch, the smallest size is 34 pixels. And then in that batch, your size is 34. And that's, if your network is fine with different sizes, only that inside of a batch you need a fixed dimensionality, then you can have even different dimensionalities across different batches. And then you can use collate to make sure that at least inside of a batch you have always the same size. You cannot do this inside the get method of the dataset, because there you don't know what's the shape of the other instances. This is also where you need collate. Okay. Okay, good. Only a final case. What happens if we can put the data into the memory? Because my database is 20 gigabytes big and I don't have so much space in my machine. So then we need to do something yet different. Nothing of what we have seen so far would work then. Okay, what you could do would to use the dataset class and say, well, I don't know the full dataset in the beginning, but every time that the data loader tells me, give me instance number 15, I look in which file do I have number 15, because I split my 10 gigabytes up into 10 times 1 gigabyte. I could do this. I could split my 10 gigabyte up into 10 CSV files of 1 gigabyte each. And then I know, aha, instance number 5 is in this CSV file. Instance number 30,815 is in this CSV file. But imagine the cost. So you want to compile a batch of 32 instances, and the data loader asks you 32 indices. And you will every time load a 1 gigabyte CSV file only to extract one row. This is completely ridiculous in terms of runtime. Okay, so the problem is that you don't know which indices will be queried. You have random access to the instances, and this is why you should really not do this. So in theory, it's possible, but it would not be a good solution. What you should do is to use an iterable data set. So this is this second type of data set that Pytorch allows. You have map style and iteration style data set. The difference is simple. In the iterable data set, you don't have a length. So this here is a repetition of what we saw before. The iterable style data set does not have a length attribute, but just and also no get item. It just has an iter. So basically, it only says the only thing that you can do with the second type of data set is give me the next instance. You cannot say give me the 15th instance. Only next, 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 next. Now, if you can only say next and not access specific instance, you don't need a sampler anymore, because the sampler gives you the indexes you want to know. But if you can't access the indices, you will not use the sampler. So the data loader, in this case, does not use the sampler. But what else is interesting here is there is no notion of epochs anymore. Because one epoch is I see all the database once. This is one epoch. But if my database doesn't have an end, because it is a stream, and you can always get a next element, then there is no such thing like an epoch.
I think that that's the kind of data set that you're going to use if you're managing, for example, financial data that's like always coming out.
Yeah, it can be because your data already is a stream, So if your data originally is a stream, you can use this, or if your data is tabular, but it's so huge that you cannot use the dataset approach anymore. Yeah. So in this case, what is an epoch? You define it. So in the train loader, you say, okay, iterate over the iterable data set. Give me the next batch. The point is that this will iterate forever. Because this data stream will always give you new batches. So you can manually at some point, like after 100 iterations, you can say break. You manually stop this loop and say, okay, that was now one epoch. We saw 100 batches, that was one epoch for me. And then you go again, and you get, okay, so then you have to implement these epochs by yourself. It's not like part of the framework anymore. Good? Okay, very good. So in this case, the figure would look like this. Almost the same, but the sampler is gone. Okay, the sampler is gone, and we don't call the get item, but the next. Okay, the next function here on the iterable data set. And he somehow decides internally which item will be the next. He does that, or you use it. So if you inherit the iterable data set, then you use it. And of course, there would be a very nice Gradescope exercise where you can practice this. So this is then the overview of getting into touch with data and making sure that we can load whatever data we want and do forward pass or something on whatever data we want. No matter whether they have missing values, categorical values, whether the instances have different lengths or shapes. We can do all of this. We only need to know where we have to do it inside this framework. I hope that got clear today. I thought that we would finish super fast. Okay, we did not finish super fast, but I also hope it was not too fast. And we have nice exercises for you at home waiting. So enjoy and see you next week.
Could you share the
Sure. And what you have here, I have the decision diagram, and I first want to make this nice before so I have a decision diagram that tells you in which situation should you use which of the four strategies.
and many the notebooks?
Yeah.
Lo puedes considerar.
Muy bien. Hasta luego, chicos.
Gracias.
Emilio,
Hasta luego, muchas gracias.
Que estaba haciendo, estábamos
Sí, hasta luego.